Hello, welcome to Biochemistry Simplified. My name is Dr. Elik and I'm reaching you today this morning. Want to say happy new year. It's been a long while and today we'll be looking at acid and bases, and particularly we want to begin by looking at acid-base chemistry. So acid-base chemistry are profoundly important. Acid-base chemistry are profoundly important, and we're going to going through what we already know, basically general chemistry. We're going to be talking about pH. We're going to be talking about how acids and bases behave, and the idea that the only thing that moves around in acid-base reaction is actually the proton. All right, so let's just get started. You want to concentrate on this aspect and use what you know, that is the information from your general chemistry, to understand a huge amount of biochemistry, irrespective of the details, examples that will be given out in this lecture. I just want you to understand that the only thing that moves around in acid-base reaction is the proton. Actually, the proton, which is generally known as the H plus. So let's just get started. We want to begin today by looking at water. How do water behave in solution when it dissociates? So let's begin. Let's begin with water. So we have H2O. So we want to look at water, and water in solution actually dissociates a little bit, and it releases a free hydrogen and a free hydrogen. So a free proton, which is your H plus, and a free hydroxide actually, which is your OH minus. So when you have water going into aqueous solution, so in aqueous solution we have, oh sorry about this, so in aqueous solution water actually dissociates, but it dissociates a little bit into what we have as the proton, and this proton is freely floating around in solution, and we have the hydroxy group, which is also freely floating around in aqueous solution. So from our general chemistry, we want to be able to have some sort of numerical measure to an extent to which something dissociates. In other words, how much, the amount we're actually concentrating on, the amount of the proton, which is your H plus, or the hydroxide or hydroxy group, which is your OH minus, that is floating around in water. In other words, we want to have something called the equilibrium constant. And in doing that, you have a reaction as follows. So to get the equilibrium constant, you have so to get the equilibrium constant, you have the following. So you have water in water as aqueous solution, and that dissociates into a proton H plus OH minus in aqueous solution. So that's pretty the reaction, and that gives you an equilibrium constant, which is the concentration of the product of this reaction. So you have H plus and OH minus, and that's actually equal to Kw, which is your water constant, and this actually has a value of 1.0 times 10 raised to minus 14 at, this is actually at 25 degrees 25 degrees Celsius. So that's basically the equilibrium reaction of water. So this actually shows, sorry, I need to write this again. So you have OH minus aqueous. All right. So that equation, which is actually this equation right here, is a very important relationship that tells us the constant, or shows us that most of the proton, which is the H plus, stays in water and a little bit dissociates in water as what? OH minus. That said, we want to see in the next page a very important thing to note. So let's go to the next page. So I like to do this with a different color of pen. Let's say red, because we want to note down something. So we say notes. So note that in any and every aqueous solution, what you have is the concentration of the proton, which is the hydrogen, increasing. So we just do this with this arrow, and that of the hydroxy group, which it dissociates into, it decreases. And this concentration is actually equal to 1.0 times 10 raised to power minus 14. In other words, if this H concentration of the H increases for any reason, the concentration of the OH minus decreases, such that their concentration has to be equal at the equilibrium constant. Their product does not change. If one goes up, the other comes down. So let's introduce something we call the P scale. P scale. So what is P scale? Like P scale, you already know P scale. So P scale is describes the pH as the negative logarithm of the hydrogen ion concentration. So P scale describes all of this. It describes, so when you talk of pH and looking at P scale, you look at the negative logarithm of the hydrogen ion concentration. you can also have the POH, and this will simply describe the negative logarithm of what? The hydroxy ion concentration. And you can also have the P chloride, and this also BCl. This also describes the negative logarithm of what? The chloride ion concentration. So it actually could be P anything, and that describes the negative logarithm of whatever it is that you are looking at. So, however, looking at the P scale, most of the time we talk about pH, which is the hydrogen ion concentration is chosen as a standard against which other things are measured. That's important to note down, and I like to do this in blue. So, yeah, taking my pen. So now we just say like MB to note. However, looking at P scale, most of the time we talk about pH. Looking at P scale refers to pH most often. Refer to pH most often, and in this case, pH is implies the hydrogen ion concentration. Hydrogen ion concentration, and this has been chosen. So it's chosen as a standard. It's chosen as a standard against which other things are measured. As a standard against which other things are measured. Standard against other things are measured. Great. So H hydrogen ion concentration are generally very small. They are very tiny numbers, like 2.6 times 10 raised to power minus 3. So instead of dealing with those tiny numbers, they developed the idea of P scale, because they want to deal with numbers that are more natural, like 6.2, 7.4, etc. So you can use the concentration directly if you wish. It does not really matter but in biochemistry, they tend to use P scale most exclusively. So we look at their reaction in the and some example in the next slide. So thus, looking at the basic reaction, having established why P scale was created because of the tiny numbers we want to know and use in biochemistry, numbers that are more natural in biochemical reactions. Now, you say, thus, we have hydrogen ion OH minus, like we have established, this is equals to 1.0 times 10 raised to power 14, and that shows what? Your equilibrium constant. Actually, all of this here also implies, simply means pH plus pOH is equal to 14. So the whole of this deals with concentration directly. The whole of this deals with concentration directly, while pH plus pOH, as seen here, okay, deals with what? A different representation of concentration. This deals with a different representation of concentration. Of course, between here and here are basically the same. So we've established that concentration of hydrogen ion in that of hydroxy ion is actually equal to 1.0 times 10 raised to power minus 4. And that simply implies is the same as pH plus your pOH is equal to 14. Remember, this is the equilibrium constant of the hydrogen ion concentration and hydroxy ion concentration from the dissociation of water. And we say that the pH, which is the negative logarithm of hydrogen ion concentration, and pOH, which is the negative logarithm of hydroxy ion concentration, is also equal to 14. Now we want to look at example. So we say example 1. Example 1. So in this example, we want to look for the pH of glycine, or the pOH of glycine in solution. The pH of glycine the pH of a glycine solution is measured to be 5.4. The question is, what is the hydroxide ion concentration in the solution? So in solving this example, should I do this in the next slide? So note your question. The pH of a glycine solution is measured to be 5.4. 5.4. What is the hydroxide ion concentration of this solution, or in this solution? So we want to look at how to solve this next slide. So in solving this, we take the solution of that question. So in solving this, we must just use the basic relationship. In solving this, we just use the basic not must, we could use other method. So we just okay, so we just use the basic relationship, which is hydrogen ion concentration with hydroxide ion concentration is equal to 1.0 times 10 raised to minus 14. We were given the pH of this solution to be pH is equal to 5.4. So if we look at pH, we say that pH is equal to the minus log of hydrogen ion concentration. So this implies that pH, which is 5.4, is equal to the minus log of what? Hydrogen ion concentration. So this here simply describes the definition of pH. All right, so we'll go ahead. Let's go ahead and take the antilog. Let's take the antilog. So taking the antilog, we have hydrogen ion concentration, which is this one here. Okay, hydrogen ion concentration, all right, is equal to the antilog will now be 10 raised to the power of minus 5.4, and that gives you your 3.98 times 10 raised to minus 6 molar, or moles per liter. Now, taking the antilog, this is what you get. So we also know this other relationship that the hydrogen ion concentration and that's applying the relationship we used, which is here, is equal to 1.0 times 10 raised to power minus 14. So to get the hydroxide ion concentration, which we are looking for, is to do like a change of subject formula, and what you simply have there is your concentration OH minus is equal to 1.0 times 10 raised to minus 14 divided by, of course, the concentration of the hydrogen ion concentration. We have it here as what? 3.98 times 10 raised to power minus 6. Okay, so when you simplify out that mathematics, what you have is 2.51 times 10 raised to power 9 molar. 9 molar, and that actually gives you the concentration of your hydroxide ion, which we are looking at. So this is simply the answer to the question. All right, so note that to get the pOH, like we have the pH is 5.4. Now you know the concentration of the hydroxide ion concentration, that's OH minus concentration. You can simply get the pOH from by simply taking the negative logarithm of the OH. So if you want to get your pOH, sorry about that. Okay, so let's do that in the next page, trying to get the pOH. All right, so we just move to the next page. Now if we want to recap on this page, we have gotten the concentration of the OH minus to be what? 2.51 times 10 raised to power minus 9 molar. That's what we established, which is actually the answer to the question. Now we have pH here given to be 5.4, and with that we got the concentration of the hydrogen, and we're able to get the concentration of the hydroxide. Now to get the pOH, which is the negative logarithm of what? The hydroxy ion concentration. And the hydroxy ion concentration, as we can see, is 2.51 times 10 raised to power minus 9 molar. Now, if you take the antilog of this, we have pOH is equal to 8.6. Now, we gave another expression earlier of how we can represent this concentration, and we said it can also be represented as pH plus pOH. So I'll just write recall here. pH and pOH is equal to 14. Just using this representation, you can actually also get the pOH, because pH is given as 5.4 plus pOH, which is equal to 14. Now, if you make pOH the subject of the formula, what you simply have is 14 minus 5.4, and that also gives you what? 8.6. Okay, so that's pretty the explanation and expression of what that example is showing. So in our next slide, we want to quickly look at the pH scale in itself. We looked earlier at the P scale. Now we want to look at the pH scale. Let me use green for this. So we look at the pH scale. So the pH scales basically show the range, the scale that comes from 0 to 14, and what shows acidity and what shows basicity, and of course the neutral. So for pH scale, you have pH value ranging from 0 to 7 as what? As acidic solution. In this case, hydrogen ion concentration is greater than hydroxide ion concentration. Then we have a pH scale of just 7, where this implies a neutral solution. And in this case, we have hydrogen ion concentration, which is your proton, is actually equal to the hydroxide ion concentration. And we have a pH scale of 7 to 14. And what you have here is what? A basic solution. A basic solution. And what you have here is showing that your hydrogen ion concentration is actually less than your hydroxide ion concentration. Or you could reverse it to say hydroxide ion concentration is actually greater than the hydrogen ion concentration. So note that the scale comes from 0 to 14. So note the scale comes from 0 to 14. And that is actually concentration 10 raised to power minus 7 over concentration 10 raised to power minus 7 is equal to 10 to the power of minus 14. So no matter what they are, whether basic or acidic, they will multiply and equal to 10 raised to power minus 14 at what? 25 degrees centigrade. Thank you. So we'll stop here. In our next set of lectures, we begin to look at strong acids and strong bases, what they are, weak acids and weak bases, what they are, and their importance in biochemical reaction. Thank you for listening.